Welcome back. In the last two lectures in the particular topic of entropy, we discussed that entropy is a property, is a state function. And in this particular lecture, we'll be talking about a bit of more details of the entropy, and as well as calculate the entropy changes for the case of incompressible substance, ideal gas, and develop some property relation for some processes, which we will call asentropic processes. So what is entropy? Entropy is nothing but measure of disorderedness. We already discussed that if you have an isolated system, the entropy change of the isolated system should continuously increase or remain constant. So the entropy change will be zero, or there will be no change in the entropy if it is a reversible process. Otherwise, for any isolated system, if it undergoes a process, the entropy should keep increasing. Okay. So entropy is related to the disorderedness, is the way the molecules arrange themselves, the probability of having more possibilities in a given system. So let us just look at first how the entropy change with the state. So as I already mentioned, the level of molecular disorderedness, which we describe in terms of entropy of a substance, increases as we increase the temperature. So with solid to liquid and to gas, this is an indication that the kinetic energy of the molecules of these different states or phases increases with as we provide more temperature. That means the kinetic energy of this is quite high compared to the liquid, which essentially means this is more disordered compared to the case of the solid. Okay. Now, having higher kinetic energy of the molecules is not an indicative of usefulness of the energy. Okay. This is quite you can understand if you have a container having gas with a high kinetic energy, and you put, for example, paddle or shaft, a higher kinetic energy of the molecules do not cause rotation of the shaft. So essentially, even though energy is high, it's not yielding any significant usage of the energy. Okay. So that's what we say, that disorganized energy, which would be the case of the high temperature case, does not create much useful effect, no matter how large it is. And certainly the molecules start reducing its translation energy with the reduction in the temperature. So if you reduce the temperature and bring it to the solid, the molecule translation of the kinetic energy is much less. And here in the case of the solid, molecules evaporates. Okay. And particularly when you have a pure crystalline solid and the temperature is zero, so overall the vibration minimizes for the pure crystal. And in such case, when you have a perfect order, that means the particles or the molecules are sitting on the lattices. Okay, it's the entropy is considered to be zero because there is no disorderedness. Everything is ordered in that sense. Okay, so this becomes the reference. So anything you consider T equal to 0 Kelvin as a reference and calculate the entropy of any substance which is higher than temperature 0 Kelvin would be an absolute entropy. Okay, and this is what turns out to be the third law of thermodynamics, where we say that a pure crystalline substance at absolute zero temperature is in the perfect order. Okay, and its entropy is zero. Okay, now as I said, that entropy essentially can be related to the disorderedness, in some sense how the specific possibilities of the configurations or number of the configurations of the molecules in a given state. So having higher temperature indicates higher possibilities or number of the configurations, because molecules can move around, so they can access possible energy levels. As we know that you have different energy levels, these are different energy levels, and the molecules can sit on the ground level at a very low temperature, and you provide a kind of energy, it will excite to the higher energy level. Thus possibilities of different energy levels increases at higher temperature, which would be the case of the gas, and essentially which means that you can have more possible configurations. And this is entirely now is related to some relation which we call it Boltzmann relation, which relates S by K is ln of omega, where omega becomes the number of possible configuration, where S is entropy and K is Boltzmann's constant, which the value is given here. Okay, so we can try to relate this just to understand a bit that for a given process, if it to occur, the entropy should increase or at least remain constant for the case of the reversible. It should increase for non-reversible or any particular process. So let's consider the case of unrestrained expansion or free expansion of the gas, and try to see if we can make use of this expression. So if you consider a box, okay, where this is, let's say, a partition, okay, and this is a kind of room box where the gas is there, and in order to make use of this expression, what we are going to do is we are going to divide this let's say into some kind of a lattice or this arrangement where the particles can sit in it. So let's say we have 3 particles and they can fill this place, and they can of course fill many possible, all these places, which is the boxes, and these are the possible arrangements. And similarly you have other room also in a similar sense, and this is your partition. Again, as I said, this is your partition. So this is before the expansion, the gas was here, okay. So what is the possible arrangements of the gas molecule? Let's say we have 3. So the possible arrangements, if we define as omega A, this becomes, there are 9 initial possibilities. Let's say box 1 and this is 2. So this is 9 factorial divided by 3 factorial, and then the rest is 6 factorial. 6 is of course the empty regions, and the other case, of course, there are 9 lattice, these regions, we can say this is nothing but lattice point, okay. And this essentially there is no particle in this particular second box, and hence this essentially would be 9 into 8 into 7 divided by 6. So that becomes your number. So this is your 3 into 4 into 7, okay. Now you take out this partition, you allow this gas to expand. What you see is a condition of, let's say, B. B is a final state, okay. So B is the final state. In this final state, what is the possible number of configuration where the molecules can arrange themselves, and this would be omega B. Now you have 18 lattice points and 3 is number of particles. It has more possibilities, which you can clearly see, okay, and thus you have the following number, okay. So this is your 3 into 7 into 6. Clearly omega A is less than omega B, which essentially means that the number of possible configuration for the case of B after expansion is much larger. Essentially this indicates SB is much greater than SA, okay. And this is what tells you that your delta S is greater than 0 for this simple exercise. So what we did was we connected this S entropy change to the molecular disorder, which essentially we represented in terms of the number of possible arrangements in a given box, okay. This is a way to understand macroscopically the entropy change for a given process. Let's little bit look at more into details of different types of processes and how does it cause changes in the entropy. As we already discussed, that the entropy change is either due to the heat transfer or due to the irreversibility. Irreversibility would be due to frictions or unrestrained expansion or any finite temperature based heat transfer or temperature gradient based heat transfer, okay. So let's consider this rotating shaft. Now the molecule of this rotating shaft is quite organized. Consider this solid here, it's rotating in a specific way, and by considering this to be a frictionless, this particular organized way of energy can be used to perform tasks such as raising weight, okay. And thus this is a kind of energy which is an organized form of energy and is free of a disorder or entropy, and thus we say that the work is basically an organized form of energy, and this is for this particular form of energy there is no entropy transfer associated with energy transfer as work, okay. So there is no entropy change and there is no degradation of energy in this kind of operation, in this kind of process. But now if you consider anything related to the heat, you will see significant degradation of the quality of the energy, okay. Okay, so let's consider this as an example. This is a case where a paddle wheel which is worked on this gas. By doing a work on this gas, the temperature increases, considering the internal energy increases because the conversion of the work to the internal energy occurs. In this case, increase in the temperature, we know that increases the disorder, okay. So higher the level of disorder at higher temperature, that we already touched upon in the previous slide. Now hence the organized form of energy, which was this, got converted to disorganized form. So by conversion of the internal energy and raising in temperature, which essentially means that if you want to convert back this disorder to the ordered form, only a small portion of this energy can be converted, and you have to make use of the heat engine. Okay, so as we discussed already that the quantity of energy is preserved, but quality of the energy is bound to decrease as during the process. Okay, and this decrease in the quality is accompanied by the increase in the entropy. So if entropy is being generated, which essentially means the quality decreases, or in other words, if entropy increases, it essentially means the quality of the energy decreases. Okay, so let's consider this case, which is associated with the heat transfer. Okay, and this is specifically a heat transfer from a hot body to cold body, and let's say you have a 10 kilojoule which is transferred from the 80 degree Celsius body to 80 degree to 20 degree. Okay, now you can do analysis of your entropy of this combined system. Your delta S, considering to be this is a reversible process, then we can write this as minus Q by TH plus Q by TL, and so the Q is of course let's say 10 kilojoules. Minus is because this corresponds to loss in energy, and plus of course is gain of energy. Now TL is low, so overall this can be written as Q 1 by TL minus 1 by TH, and since TL is less than TH, your delta S is greater than 0. So thus the combined system, the entropy is of course increasing. So we can say that some disorganization flow with the heat. Okay, so there is a flow of heat or the heat transfer, and thus entropy is increasing of the system. So there is a disorganization along with this heat flow occurs, or in other words, heat is a form of disorganized energy. During a heat transfer process, the net entropy increases. This we can now clearly see. Okay, the increase in the entropy of the cold body is more than the decrease in the entropy of the hot body. So essentially the cold, this increase in here offsets the decrease in here, and thus it increases the overall entropy. Now there is another important aspect, that though the 10 kilojoules got transferred from a hot body to the cold body, and we know that the quality of the energy decreases with the decrease in the temperature, that was based on our efficiency analysis of a Carnot cycle or in general for any devices. So we clearly said that the lower the temperature, your efficiency is lower, and higher the temperature, the efficiency is higher. So at the end of the process, this 10 kilojoules of the energy transfer is at the low temperature and thus at low quality. Okay, so let's now derive this TdS expression. First connect this entropy change to the other properties. So we can start with basically the reversible process, particularly the internal reversible process, and we can start with your first law of thermodynamics. So let me write here dq internal, let's say reversible, okay, minus del W, again internal reversible. So this is the heat in, and this is of course out, is equal to change in du. So this is for closed system. Okay, for internal reversible or reversible, you have this TdS as an expression, and this is your PdV. Thus you can write TdS minus PdV is nothing but du. Okay, now this expression, though we have derived for internal reversible case, but note that the du on the right hand side is a state function. Okay, and these are all state functions, these are properties. So it depends on only the state of the system. So thus the change in the delta U, this expression is valid for irreversible as well as the reversible process. Okay, though TdS will not going to be del Q for the case of irreversible, but this expression tells you that the change in the internal energy can be written in this form. Okay, now I can write this in this form. TdS is du plus PdV. I can also write in per unit kg. Okay, so this will be your kilojoules per kg, this will be your kilojoules. Okay, now this becomes your first Gibbs expression. So this is nothing but Gibbs equation. Okay, you can extend this exercise for the case of enthalpy, considering that enthalpy is nothing but U plus PV. Okay, so you can come up with dH is nothing but du plus PdV plus VdP, and this is nothing but your TdS. Okay, thus your TdS is dH minus VdP. Okay, so this is another expression, or another Gibbs expression, second TdS expression or relation. Okay, you can summarize this in terms of ds in differential form as du by dt from here plus pdv by t, and for the case of enthalpy, okay, you can write in this form. Okay, so this expression are going to be used for our analysis for ideal gas and other cases. Okay, so these are the two specific expression which is quite useful for our other analysis. So let's look at this. We'll start with this first equation. Okay, and du by t plus pdv by t, and we can write this here. Now our interest is to find out the entropy change of liquids and solid. Okay, for the case of liquid and solid, which we'll be considering incompressible fluid, your change in the delta V is going to be 0. Okay, and thus we can write this expression in this form, simply du by t, and since we know that for liquid and solid this can be written as simply the C and dt, considering the C is constant whether it's for the solid and liquid. Okay, so this is a common constant specific heat, and then you have this, the du is equal to C dt. So you can replace here, okay, and then you can integrate. So that becomes your change in the entropy, and this is integration from 1 to 2. Now we have already discussed earlier that specific heat for liquid and solid depends on only the temperature. You can express this in terms of average specific heat, and then the expression will come out to be simply the log of temperature ratio T2 by T1. Okay. Now if you consider an isentropic process, which means that the S is constant, okay, for this liquid and solid, which is incompressible fluid, which essentially means from here we can consider this to be 0, which indicates clearly that this is for isentropic process would be a constant temperature process. That means it should be also isothermal process. Okay, this is a clear derivation based on our assumption of this. Okay, now we can extend this analysis for the ideal gas. We know for ideal gas your PV is equal to RT, and the relation of change in the internal energy can be written as in terms of your specific heat at constant volume, change in enthalpy in terms of Cp. And we start with this first relation, which is this, and we also written here as the second relation for in terms of enthalpy. Okay, so we can write down the expression of du here. So du would be in terms of Cv dt, and we can also rewrite in terms of so that we get only the temperature expression. So we can also place this in terms of volume so that we can integrate easily. And now it's written here, so du is written as Cv dt, and P by T is expressed in terms of R by V. Okay, so thus your expression of for the case of ideal gas is clearly written in this form. The change in entropy is this term plus this term which relates the change in the volume. Okay, similarly you can do the exercise for the using the second expression, which relates enthalpy and the pressure to the change in the entropy, and this is your Cp dt for the change in enthalpy, and then again you make use of ideal gas and you get this expression of entropy change in terms of Cp T dt by d, and then you have this pressure ratio in log form. So these are the two contributions now. So depending on the problem statement you can make use of this expression accordingly. Okay, so let's look at specific cases where we can consider specific heat as a constant. Okay, and for the exact analysis where you have exact information of the entropy. So let's look at here for the constant heat approximation. So Cv will be taken at an average temperature, so this becomes Cv average. So this is Cv average at T average. Okay, and similarly for the same for the Cp average. So essentially it means that you are taking the Cp at a specific T average. Okay, now you can write this in terms of unit mole basis. Okay, so there R will be Ru, and we have used these bars indicating a unit mole, and this is the same for the case of the second Ts relation based change in entropy. We talked about approximate analysis. We will consider now the exact analysis for the case of entropy, where the entropy is calculated based on the absolute 0 as a reference, where the temperature T equal to 0 is considered as a reference, where the entropy value of that is going to be 0. So S here is simply 0 to T Cp T dt, okay, which essentially means here for the reference case S is 0. Okay, so this becomes your absolute entropy in a calculation, and this is given in table A17. Okay, so now if you want to take a difference between S2, S1, this indicates based on this absolute 0 as reference, this becomes simply this relation. Okay, so this is only connects the temperature difference, nothing more. So but of course we know that S is depends on temperature and pressure both. Okay, so because you have this relation AS here, so this is one part, okay, and this is another part here. We will consider the pressure part. So here this is one part and this is another part. So if you are considering this based on this analysis, then you can rewrite this expression of change in the entropy for unit mass in terms of in terms of your absolute 0 as a reference temperature. That will be the change in the entropy plus the other part, which is a contribution due to the change in the pressure. Okay, and this similarly for the unit mole you can write in this form. So that is based on the exact analysis of a specific heat, where we have calculated the entropy, absolute entropy based on the reference 0 to Kelvin. Okay, so now we will consider a specific case which is asentropic process for the ideal gas, and we will connect this to polytropic process. So we can start again with this expression, okay, one of the expression, and consider this to be 0 for constant specific heat. When you consider this to be 0, so you can rewrite this expression in this form, okay, where CV here is of course the CV average. Now you can rewrite this expression, take it here, and it goes to the power, and this can be rewritten as considering that R is Cp minus Cv and K is the ratio of the Cp, and thus your R by Cv, which is this, is nothing but your K minus 1. So you can rewrite this expression in terms of this. Okay, so this can be written as in terms of this, because logs can be taken out, and this can be written as into K minus 1. So this is one expression based on a constant specific heat analysis, and here we have considered isentropic process, because that means the entropy is constant. You can change the variable because this is ideal gas. You make use of PV is equal to RT, okay, and come up with a different kind of expression, which is what is written here. So this is expression based on ratio of the P, or you can connect the pressure ratio with the volume ratio. Okay, so these are three different individual expressions. Okay, and thus you can summarize this, that for isentropic process of an ideal gas, this expression holds. These are all constant, and this is true for ideal gas, isentropic process, and constant specific heat. And if you recall, this is nothing but your expressions which we have written earlier for polytropic process, where gamma or K, sometimes we write also gamma, is nothing but Cp by Cv, and Pv is equal to nRT is constant was the case of polytropic process, where n was considered as simply gamma or K. Okay. Now this is the expression which we calculated for adiabatic causes static equilibrium, or in this case isobatic reversible case. It also tells you that isentropic process is nothing but adiabatic reversible process for ideal gas. So with that we will do just an example and finish up this lecture. So this is an example of air compressed from an initial state of 100 kilopascal and 70 degrees Celsius to a final state of 600 kilopascal and 57 degrees Celsius. What we need to find out is entropy change of air during this compression process by using the property table, or by considering the average specific heat. If you want to use the property table, we have this expression which connects the change in entropy to the change in entropy first calculated from the absolute 0 as a reference, and then the contribution due to the ratio or change in the pressure. And from A17 you can directly take these values, considering the values are given as far as the temperatures are concerned. So temperature is needed for this part, and of course the pressure will be used for this part. Okay, so with that the value comes out to be this. Okay, and for the second case you have this expression, and Cp average will be calculated at an average temperature, that means 17 plus 57 divided by 2, which comes out with 37 degrees Celsius, and with this the value comes out to be this, which are very close enough. So this is something which we can use. This was the illustration of making use of the table and average specific heat for calculating change in entropy. Okay, so with that this will be the end of this particular lecture. So in the next lecture we'll discuss the reversible steady flow work relation and other steady flow devices and the corresponding isentropic efficiency of those devices. Okay, so see you in the next lecture.